It's not muted anymore. Okay, let's hope this works. It seems I'm not getting other people here. So maybe the link is stale again. I don't know. I'm going to record this by myself then. And we'll have the lecture here now. Okay, going to start here with this with my slides. Today we're going to talk about random distributions. So very often the case, before we go to particular distributions, I mentioned something about samples. So, we've talked about the theoretical concept of sample space, meaning that those are the possible values that you can get when you execute or carry out a random experiment. And when you do the experiment, you will get some value, and that is in your sample space. The thing is, if you carry out the random experiment many times over, you get what we might want to call a sample. The sample consists of not just one, but maybe several values. So we repeat the experiment several times, and then after that, we kind of analyze the outcomes, not just one outcome, but all the several outcomes, and maybe we can get an idea about how the distribution works, or what kind of properties does the distribution have. So that's the topic of today's first topic of today. We may have other methods by which we study the outcomes of the random variable. So for instance, we may carry out some random experiments, but maybe we can have some reason to believe that these random variables are the product of some, I don't know, some other method or some process by which we can then conjure up these values by other means, not just by analyzing the random outcomes themselves. That's not really an issue here. So let's say that we have some experimental values of these random variables. We may draw some conclusions about probability measures in the sample split. So maybe if we sample it enough, we can get some kind of idea of how common certain values are. So this boils down to the probabilistic, the frequentist idea of probability. So in the frequentist, remember that in the frequentist approach to randomness, the idea was that I'm having trouble with one of this. Just move this about a little bit and move that about a little bit. So in the frequentist idea, the probability of an event is considered to be its relative frequency over the long run. If we do a very, very large number of experiments, and we consider that the event occurs some f times, and we consider n the number of experiments we make, then f over n is considered to be the probability of that event as n approaches infinity. So we can't say that it's f over n for any particular n, but we would expect f over n to be closer and closer to the probability of the event as n grows. So here we have the idea that very common way which we describe or approach this is that we divide the possible values into events, xi, event 1, event 2, and so forth. And then we observe how many times these events occur and their frequencies. And then we have the relative frequency, which we denote as pi, meaning that that's our idea, rough idea about the probability of this event I. Okay, we had one participant and now we don't have that anymore. And so this morning is not going to be very popular. So there are some things that we might want to say. So if we have a random variable and a sample of n values x1 to xn, then we define the sample mean and sample variance as the sample mean is simply the average of all those values that you get. And the sample variance is the average over the square of the distance from the sample mean. The divisor here is n minus 1 and not n. And if there were more participants, I would like to ask, why do you suppose that this is n minus 1, that is divisor here, and not n? The reason for this is that consider the very simple situation where you have two different values, or just one value. If you have one value, then it doesn't really make sense to talk about the variance. It would always be 0. On the other hand, if you have two values, then this is a measure of how far they are from their average. If you have two values, then it's just add those two together. You can argue that you should divide it by 2. We can argue this over and over again. Later on, we will see is that these are what we will later on describe as estimators. Estimators meaning that these are kind of statistics that we calculate from samples, which we can then use in place of a value that we do not know because we don't know the exact distribution. And the sample mean in this case is a estimator of the expected value. As you would, the way we describe the expected value, that we describe the expected value as the tendency, where the values tend to go on average. And that's exactly what the sample mean is average over all the sample, over the whole sample. On the other hand, the sample variance, it has a slightly different tune to it. We can argue that you'd have to divide it over 1 over n and not 1 over n minus 1. It turns out that this sample variance has the expected value that is equal to the variance of the distribution. And if it's 1 over n minus 1, then that, if it's 1 over n instead of 1 over n minus 1, then what you will get is you will get something that has a slightly lower expected value than the actual variance is. So this is what we call an unbiased estimator. This is not yet the topic here, but we'll talk about it later a little bit, and I just wanted to mention it here. One way to argue that you should divide by n minus 1 is that because if you have this average here, then it already contains information about all of those. So there are really only n minus 1 independent values here because if it's just 1, then there are no independent values. If it's 2, then they depend on each other. This is what we call degrees of freedom. Again, something that's probably not going to be very deeply discussed during this course, but you will encounter this term degree of freedom later on in this topic if you study statistics and probability theory, especially statistics. Then you will encounter this concept of degree of freedom. You can think of it as how many independent values are there. So in this case, once the average or the mean is fixed, then that fixes one dimension, if you will. All right, let's move on. The sample standard deviation is simply the square root of the sample variance, like the standard deviation is the square root of the variance. If we, instead of observing particular values, we might be observing certain categories of representative values xi to xk, and then they have these frequencies. They, xi appears fi times. So this mean is simply fi times the value xi, how many times does it appear, and so forth. Oh, there's a typo. That should be k, not n. Then don't mind about this. I'll fix that later. So let's give an example. Here we have 100 measurements of time. A component is functional. So we have some component, let's say transistor or a capacitor or something like this, and it's something that is crucial to the functioning of some machine, and we observe that sometimes one broke in 0.24 years, one in 0.62 years, and so forth. These are all random variable values of the variable that describes how long the actual component lasts. And let's say that we categorize these, because these values are very hard to visualize or think about these directly, because these are real numbers. Sorry, my yawning. These are real valued numbers between roughly between 0 and 8. So we categorize these into categories n minus 1. So if it's over if it's some non-negative integer n, but less than n minus 1, that should be n plus 1 here. Seems I've made a lot of typos here, so I don't download the slides yet. I'll fix that. I'll fix that slide. It should be n plus 1, not n minus 1. So let's move on. So here we calculate how many times. I'm not going to bother you with doing that by hand. So we notice that those values that are between 0 and 1 not included, occur 39 times. Because there's 100 measurement, and the relative frequency, or the PI, the approximate probability that we get from here, is 0.39 for the component to break within the first year. This capital F here is the cumulative frequency. So 39 cases are broken within the first year. And then 21 are broken during the second year, giving us the probability of about 0.21 of a well, this is our approximation, or the idea of the probability, the 0.21 to break within the second year. And the cumulative frequency is 60, so 60 out of 100 have been broken before the end of the second year. Or that from this data, it seems as though the best guess is that that 60% or 0.6 probability for a component to break within 2 years. On the third year, 18 broke down. So it has a 0.18 probability, if you will, of breaking within the year 3, between 2 and 3. Frequency, cumulative here, you add the 18 to the 60, so that's 78, and so forth. So we see here that clearly that the tendency of them to break down in the first couple of years, but then it evens out a little bit. Sorry for this yawning. This we can build a table like this. I mean, putting 100 values, here we had 100 different values. So if we have 100 different values, it's very hard to look at what's going on here, but this kind of table will already give us a little bit of information. We can also express these as a histogram like this. This is a block diagram. Here we go from just under 40, and this. The average, if we average these out, just simply add all of these together and calculate the average. It's 1.99, so an average component lasts about 2 years, except that it has a very high probability of breaking before that. And the standard deviation would be the square root of 3.18. So the sample variance here is 3.18. So the square root of that is something like 1.6, roughly, just under 1.6. So that would give us the average deviation in our data. So in software such as MATLAB or R, we can calculate these with commands such as mean x. So if in MATLAB, for example, if you have x, a vector x which contains all the values, then just mean x should give that. I really don't mind whatever software you want to use here. If you want to do the exercise and analyze those, you can use any software you want. MATLAB is perhaps preferred in the terms of that there is on-campus licenses, but given that the campus is on lockdown, use any software you want, but just make sure you understand the connection between the commands and the software and the theory here. That's really important. I fully condone and I even encourage using software to calculate all the examples and even all the weekly exercises. That's fully within your rights, and you know, it has to no detriment to your learning, in my opinion, except make sure you understand what you are doing. Modern software is very easy to use, so sometimes you can guess the correct commands and get the correct results by sheer luck, and I really do recommend against that. So understanding the theory and understanding how the theory is then implemented by means of software is in fact at the core of what I would hope you would learn. And I would rather you don't use any software commands unless you understand how that works. And I'm not going to go as far as to say that you should be able to program those yourself, but in an ideal world, you know, I'm just saying, in an ideal world, that would be the case. The thing is that I really want you guys to understand that the functions that you are using, so that, you know, but mean and variance, you know, everyone knows how to add and subtract and divide, so it's not that big a deal. All right. So these are, when we talk about mean and variance, then be careful to understand whether we mean the sample mean and the sample variance, or whether we mean the mean of the actual distribution and the variance of the actual distribution. These can be radically different. And what is even stranger is that we already encountered in the last exercise a example of a distribution that doesn't even have a mean. Well, it has a mean. Well, you can calculate the mean for every sample, but it doesn't have an expected value, and it definitely doesn't have a variance. But still, if you carry out a experiment and you get some results, so you can always calculate the sample mean and the sample variance. The thing here is that even if the underlying distribution would not, in theory, have a expected value and variance, you can still gather data if that's what you do. I mean, gather data and calculate sample mean and sample variance. There is the part where you need to be careful. You know, you have to understand, is this legitimate or is this reasonable? Well, it's not going to go there. Most of the time, this does not matter, but it really has to be understood. It really has to be understood, because random theory, you know, the probability theory and statistical analysis and the theory is often misused in very dangerous places and in very dangerous ways, so that people calculate averages, and people calculate sample variances, and then they just think that, okay, once I know these, I can just assume that the distribution is, for example, that the distribution is a normal distribution. And that, ladies and gentlemen, is a problem. It's a huge problem, both philosophically and in practice and in many other ways. I mean, let's just think about the current situation we are in, our predicament with the coronavirus and the lockdowns and you know, who knows. People are worried about societal breakdown. People are worried about hoarding. People are worried about the stock market crashing. I'm not trying to be alarmist here or cause any concern to you. I mean, I'm pretty confident that things will blow over. However, if you look at the data, for example, in the stock market currently, if you look at the stock market prices and so forth, so for a very long time, you would think that there's a clear tendency of stock prices to rise and that the variances there conform to roughly to some kind of a very nice theoretical distribution. And the last 2 weeks have shown us that that's definitely not going to be the case. It's clearly something is very radically different now than it was for the last, let's say, 5 or 6 years. So assumptions about probability theory are very often broken when applied into the real world. That's just what I wanted to say here. It goes a little bit off topic, so. Okay, let's look at some distributions. What properties do they have? We have encountered some distributions, but let's we look at some others, ones that are often more common when we analyze empirical data. We make assumptions about empirical data, and then these assumptions give us one of a couple of distributions, ones that I'm going to present in this chapter 4. So in the discrete case, the fundamental concept is what we call the Bernoulli experiment. So Bernoulli experiment seems like a pompous way of saying we do something and see if it happens. Really, that's just it. So we have an experiment that has a value 0 or 1 with some probability, and 1 is called a success and 0 is called a failure. And there's one probability associated with this. Success has a probability p, and then conversely, failure has the probability 1 minus p. So this is a Bernoulli experiment, and Bernoulli distributions are everywhere. I mean, flip a coin, toss the dice and see if you can get 5 or 6. If you can, you win. If you don't, you lose. So Bernoulli experiments are everywhere in games. Bernoulli experiments are everywhere in the real world as well. So let's say that you are going shopping. You go to some store, and well, this assumption may be broken for some people, but this is at least how I shop. Is you go to a shop and either you find what you are looking for and you buy it, or you don't and you go to the next shop. So that's a repeated Bernoulli experiment. I stop when I have a success and I continue until, if I have a failure, I continue. So here, a discrete definition. A discrete random variable x follows the Bernoulli distribution with parameter p, and we just denote it by x conforms to Bernoulli p, if it has the sample space 0, 1, and the density function, which can only be really 1. I mean, there can only be if the sample space is 0, 1, then the density function can only be something like this. You can, obviously you can denote these with different symbols, but only, there's just 2 possibilities. So if one has probability p, the other has 1 minus p. Okay, Bernoulli experiment itself is not that big a deal, but let's say that we repeat the Bernoulli experiment n times so that all experiments are independent, and then we calculate the number of successes. So, for example, we toss the coin 5 times or 10 times, and we see how many heads we get. We calculate the number of those heads, and that's our random variable. This sample space is discrete. There's values from 0 to 1. Obviously, the Bernoulli experiment can fail every time. It can, unless the probability of P is 1, in which case it's a very boring Bernoulli experiment. It can happen n times. All of them can be successful, and it can happen any number of times between them. Of course, there's a distribution arises here between 0 and n. If we consider the actual result of this experiment, I mean, the experiment itself, of course, is a sequence. So the actual repeated experiment looks something like might look something like this. So there's a 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, something like this. If there are n possible n repetition, then you have 2 to the n possible outcomes. But if you look at this, if we are really only interested in how many times the number 1 appears there, so a particular result has the success x-axis is a particular result. So a particular, like my example here, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1. So how many did I put here? 1, 2, 3, 4, 5, 6, 7, 8, 9. So n is 10. I've done n experiments now. I have 1,024 different possible sequences. In this case, I have 1, 2, 3, 4, 5 successes. And the probability of this particular thing is, I mean, it's 1 minus p times 1 minus p times 1 minus p times p times p times p times 1 minus p times 1 minus p times p. So I have the success x times, so that's p to the x, and the others are failures, so that's 1 minus p to the n minus x. But this is a particular value. But there are similar outcomes, ones that have the same number of successes. And I can pick here from these n attempts, x are successes, so I have n choose x different outcomes. So the probability of actually getting this many correct is each of these different outcomes has this probability. And there are n choose x different outcomes that have this probability. So that's our total probability here. And this gives rise to what you probably already know as the binomial distribution. So a discrete random variable follows the binomial distribution with parameters n and p. You know that x or this x follows p and p. You know that like this. If it has the sample space 0 to n, and the density function is this n choose x times p to the x times 1 minus p to the n minus x. Again, let's recap what the meaning of this is. So f of x, the density function is, this is how many occurrences there are where there are exactly x successes and n minus x failures. Right. This is known as the binomial distribution. Binomial distributions they arise in, you can think of it as they arise in situations where you repeat a certain experiment many times over. You calculate how many times a Bernoulli experiment many times over, and calculate how many successes you get. We can verify that this is a legitimate density function. Obviously, it's non-negative. And if we think about the binomial formula, which states that that a plus b to the power of n is the sum of x from 0 to n, n choose x, and then a to the x times b to the n minus x. This is from the binomial formula. And we substitute p equals a and 1 minus p equals b. Well, we get that this is in fact p plus 1 minus p to the power of n. Well, p plus 1 minus p is equal to 1, so that's 1 to the n, which is 1. So yeah, this is a legitimate density function. So we talked about the moment generating function, and this is a particular case where the moment generating function comes handy. The moment generating function can be calculated as follows. It's p times e to the t plus 1 minus p, and this whole damn thing raised to the power of n. From this, we can derive the expected value to be n times p and the variance to be n times p minus 1. So let's first look at the moment generating function. It was defined as the expected value of e to the t times x, which we can calculate, of course. We just slip in this function into the definition here. So this is that's the density function there times e to the tx, and we add over all the possible values. But we notice that e to the tx and p to the x, because we can just put this, it doesn't matter, this is a multiplication, that's a number multiplies that number, that, so we can rearrange them. Let's put this n choose x in front, and look at this e to the tx times p to the x. We can write that as p times e to the t, and that to the power of x. And now this is the binomial formula, so we apply the binomial formula. It's p times e to the t plus 1 minus p to the power of n, because of the binomial formula. So there you have the moment generating function. It's not important per se, but we can use its derivative to come up with the expected value. If we take the derivative of this with respect to t, so there's a something to the n. So the inner function here, the outer function means that's n times this, and the derivative of the inner function is p times e to the t. So it's arranged so that we put the n and p in front and the e to the t at the end. If we take this, the first derivative here, and we substitute 0 for t, then this becomes p times e to the t equals 0. This becomes 1, so p plus 1 minus p, that's 1 to the n minus 1, so that's 1. So this whole thing becomes 1, and e to the t, well, t equals 0 is e to the t, e to the 0 is 1, so the whole thing just has n times p. And we calculate the second derivative of this. Not going to go into much detail. You calculate the derivative of this and you get something like this. Substitute t for 0 and then subtract the np squared. I'm going to leave this part here. So this is this second derivative at 0 is the expected value of x squared. And if you subtract the square of the expected value of x, you get the variance. And it turns out to be np times 1 minus p. You can do the math yourself. I'm not going to go into the great detail here. But here we see a very good application of the moment generating function. It's in particular for the binomial distribution. The moment generating function is a very handy tool. It's much easier to calculate these. All right, I'm gonna have a little break, just 2 minutes now, and I'm going to continue with this